Hello, welcome back. So we're going to continue on our application. So we have an open box that is to hold 100 cubic centimeters of a liquid. We want to find the equation of the surface area in terms of x and y. Calculate the partial derivatives, the gradient vector, and use this to find the values that would minimize the surface area. So this is a really cool application problem where we're trying to minimize surface area, and then it says find D to show that this is our minimum value. Alright, so let's go ahead and get started. This is kind of fun. We're trying to minimize surface area and we're given volume. So we're going to start with an open top box. Now you did stuff like this in pre-cal, so now we're just going to apply it in calculus. This is an optimization problem from pre-cal. So I have an open top box. Now it's not a square, even though it looks like a square, but it's not necessarily a square. We don't know anything about yet. But we do know it's an open top box, and that's going to come back when we talk about surface area. So we can take a look here. If I call this, of course, x, this will be y, this will be my height, z. I am trying to minimize surface area. So this is what I'm going to take a look at. I'm trying to minimize my surface area. So I can write my surface area equation. It's open top, so I got a bottom here, which is going to be xy. I have the sides here, yz, but there's two of them, so I'm going to have 2yz plus, I'm also going to have another one over here, xz. And there's two of them, one in the front, one in the back. So 2xz. Now, why is it only xy? Only one of them. Remember, this is open, so this is an open area on the inside, so there's only one at this point. So in order to minimize something, I have to replace some variables here. And right now, there is really nothing I can replace. But they do tell me that the volume of the box is 100. So I know to get the volume of my box, that's going to be x, y times z, and that's going to equal 100. I can use this to solve for one of my variables. So let's see here. Let me solve for z here. So z would equal 100 over xy. And if I go over here, my area equation, which remember is a function of x, y, and z, my new area would be x, y, and then 100 over xy. And I can replace it. So this just becomes xy plus 2y. I'm replacing my z with 100 over xy plus 2x, and again I'm replacing my z, my z with 100 over xy. If I clean all of this up, our new area equation will become xy plus, take a look here, the y's will cancel. That's nice. But I get 200 over x plus, here the x's cancel, 200 over y. And there's my new area equation. This is what I want to minimize right there. Now they tell me to use a partial derivative, so I'm going to do that. They want me to use the gradient. So I only have two variables now, x and y. See, I've eliminated z. So when I look at my partials, my partial with respect to x, that just becomes y minus, be careful, this becomes x to the negative 1, so we get negative 200 over x squared. My partial with respect to y becomes x minus 200 over y squared. Again, to maximize this, we look for our critical numbers, right? So to get our critical numbers, we set each of these equal to 0. 0 equals x minus 200 over y squared, and we solve the system. So I'm going to solve this by saying let y equal 200 over x squared, and I'm going to plug this in. Alright, if we plug the y in, we would get the following. 0 equals x minus 200 over, and I got to square that, that becomes 400 over x to the fourth. It's ugly, but it cleans up nicely. We get 0 equals, what's that become? If I x minus, if I flip this, we're going to get 200 x to the 4th over 400. Whoop, that should have been 200 squared. There we go. Sorry, that should be 200 squared here, which I need a couple more zeros. Sorry about that. Just a couple more zeros. But they're going to cancel out anyways. Cancel, cancel. And therefore, if I bring the x over, we would get the following. 0 equals x minus 1 over 200 x to the 4th. Factoring out an x, we would get 1 minus 1 over 200 x cubed equals 0, x equals 0, and x equals, what's that, the cube root of 200. Now, even though 0 is an answer, we're not going to use it. It's kind of like boring. All right, the answer is 0, everybody. It has 0 volume. Of course, that would minimize it, but you know what? We want to build the box. Of course, 0 being a solution is one of our solutions, but it's not going to build the box, right? That won't build a box. Won't make a box. So we're not going to worry about that. So we use the x equals 3 over 200, and that gives me my x value. Now I have to find my y value. So therefore, y, remember, is 200 over x squared. All right, so this is going to get ugly fast over the cube root of 200 squared. And let's see here, what's y going to wind up being? Sorry. And that just becomes, if you simplify it, again, the cube root of 200. All right, so what do you have here? So I have my x, which is equal to the cube root of 200, my y, which is the cube root of 200, and now I gotta get z. Well, to get z, we go way back up here. Remember we said z was 100 over xy. So 100 over the cube root of 200 times, there's my x, there's my y, the cube root of 200, and that becomes 100 over, and if you simplify that, that's just the cube root of 200 squared, or you can write it as 100 over 200 to the 2/3, and that's okay to use. So, all right. So again, why not a cube? Remember, we have an open top box. If it was an open top box, it would be a perfect cube. All right, so now let's go ahead and we want to check. We want to see if this is a minimum value. Is this a minimum? For that, we have to use d, which is our second partial with respect to x, times the second partial with respect to y, minus the partial with respect to xy squared. So we need the partial with respect to x again. So if I go way up here, my partial with respect to x, there it is, that's just going to become positive 200 over x cubed. So that's 200 over x cubed. The same thing with my partials with respect to y. If I go up here, the 0, that just becomes 0. That becomes y to negative 2. So we get 200 over y cubed. And my last one, my partial of x with respect to y, that's going to be really easy. If I take my partial of x with respect to y, that's just going to become 1. Right there. All right. So now we're going to check it. So to get d, we're going to take a look at our second partial with respect to x at the point, ready, with my x value. Root 3, 200. Root 3, 200. Times second partial with respect to y at the same point, root 3, 200, root 3, 200, minus the second derivative at the same point, root 3, 200, root 3 of 200, and of course we're going to square that. All right, so basically just plug in those points. So we plug in, and we would get the following. We would get, if I plug this in, we would get 200 over, that's pretty cool. Oh, I totally messed up. Sorry. When you take the derivative, that does become 400. So these should be 400. Some of you guys probably already caught that. So let me see here. That should be 400. That's why I shouldn't take shortcuts. And that's also 400. So when we plug these in, and since I'm at the end of the lesson, I don't feel like doing a video again, we're going to leave it like that. So we can go 400. If I plug in my root cube root of 200, we get 200. Same thing over here for the y. We get 400 over 200. Like we said, if we plug in the cube root of 200 in here, we're going to get 200 minus, all right, for our second derivative, again, this is just going to become 1 squared, and that's going to become greater than 0. So we can say, since d is greater than 0, and if I look at the value of my second derivative with respect to x here, my second derivative with respect to x is also greater than 0. So that's telling me it's concave up right here. Because x is basically concave up, we know we have a relative minimum. So we can conclude that the point root 3 200, and of course our value 100 over 200 to 2/3 is a relative minimum value. Minimum, and of course this is surface area. Surface area. So if you build a can with these dimensions, you will minimize your surface area. Apologize for the 400. Well, I'm not going to go back and fix it. I'm not going to do the video again. So hope you enjoyed the video. I'll see you guys later. Bye-bye.